Oh, we're making a video, Hannah. Chemistry time. Chemistry time. Remember chemistry time? Oh, when you were in chemistry, we didn't say chemistry time because we hadn't filmed it. So how exciting for chemistry time. Let's label this. Well, we know that chemistry is the study of matter, so we'll just label this matter, and that'll cover all the bases. Let's start with your flowchart. So within the realm of matter, by the way, if our flowchart were one level up, what would be outside of matter on our flowchart of stuff in the universe? What else is there in the universe besides matter? What? Well, I want to hear someone. What else is there in the universe besides matter?
Air.
Air is matter, but that's a good guess. We're approaching. It's certainly not cheeseburger because that's made of matter.
Gravity.
Gravity is a force, but you're getting closer to the right thing. Gravity is not matter, but gravity is also not this other thing. Gravity is not really a thing at all. Nope, that's matter. You said it, I think, Hannah.
Huh?
I think you said it. What else is there?
Well, I said everything to me.
Oh, everything. No, everything isn't it. So everything's up here, and everything branches into this other thing and matter. What else is there?
Why would you just tell us?
I meant it, but I'm going to wait till you tell me.
You're trying to guess.
Oh, you know what it is.
I have to know what it is. I took.
Yeah, you have to know what it is.
But I literally just took this class last year. Give us the first letter.
No, that's not how it works. It's the thing that causes changes in this and in everything else.
Energy. I said.
Someone said it right. Energy is the right answer. I don't know who else. Energy. So everything in the universe. That's him. His name is everything in the universe. And within everything in the universe, there is energy, such as light. Right? Sound is energy. Thermal energy. Gravity, we can think of it as kind of energy, I guess. And then also matter. And so matter is what we're going to talk about. So how can we divide up matter? What are the different kinds of matter? Well, there's a couple ways we can do this. I saw a couple of examples of flowcharts in my boat. I'm going to do one, and what's another one?
Mixture.
Okay, yeah, that's the way we're going to talk about. But what's the other way people might have divided this up, which is also right, but not how we're going to talk about it right now.
Solids.
We could put solids, liquids, gases, plasma, Bose-Einstein condensate, superfluid. All of those things are true. Those are the states of matter. There are others too. Those are the states of matter. But we're going to instead divide it up this way. Hey.
Mixture and pure substance.
Yeah, mixtures and pure substances. Let's do mixtures first. What are the two basic kinds of mixtures?
Homogeneous and heterogeneous.
Homogeneous and heterogeneous.
Yeah, I kind of remember.
What are these? Well, so both have to do with genius, which means what they're made out of. You know have you heard of the Bible? There's a book of the Bible called Genesis, and that is the book where things is made. That's not how English works. That's the book where things are created, right? And that's related to this word genius. What they're made of is what this is saying. They're both made of homogeneous, homo meaning same, hetero meaning different. So in a homogeneous mixture, they're made of the same states of matter. In a heterogeneous mixture, they're different states of matter. A lot of times we say in heterogeneous mixtures, we can tell the different parts apart. But the states of matter one makes it a little bit more simple. What's an example of a homogeneous mixture then? Just an example. Say it. Oh. What is an example of homogeneous mixture? What's another name for a homogeneous mixture? Your book talks about this.
Solution.
Yeah, solution is one example of a homogeneous mixture. And then a specific example of a homogeneous mixture, we'll say, I don't want to say lemonade because that could have some pulp in it, which would be a different state of matter.
Kool-Aid?
Sure, we'll use Kool-Aid. Kool-Aid. Other brands are available. Hopefully Kool-Aid doesn't sue me. Trademark. I don't know if it's a trademark or a registered trademark. I'm sure it's a registered trademark, so we're going to change it to other brands are available. Not a sponsor. Okay. Oh, look, I even misspelled it. I definitely won't get copyright. So Kool-Aid. Okay. What's an example of a heterogeneous mixture?
Is that like sand and water?
Sure. Sand and water. Let's switch gears back up. Pure substances. What are some pure substances?
Water? No.
Well, that would be an example. Well, what are the categories of pure substances? Only.
Elements and compounds.
Yep. Elements and compounds. What are some examples of elements, and how do we tell something's an element? That thing. Yep. What's his name? The periodic table of the elements. Give me just one example from there. What's your favorite one, Hannah?
Oxygen.
Oh, oxygen's fine. But what's your favorite one, Hannah?
I think beryllium.
Oh, nice. Poisonous.
Yeah.
What does that say about you? Okay, compounds. Compounds. What are some examples of compounds?
Water.
Water is an example of a compound.
Just like the name.
What's a more exciting example of a compound? Water's pretty dang exciting. I think it's the coolest. But what's another exciting one?
Compound?
What's another example of a compound?
Iron oxide.
Sure. Let's specify. Let's say iron 2 oxide. Okay. One last thing that kind of confuses people about this is obviously we can find these on the periodic table of the elements, so they're the elements. But it kind of I need to zoom this in. Sorry. Oh, what do I press? I think this one. Sometimes people can get confused between a solution and a compound. But the key thing to remember is that a solution can have, maybe not any, but it can have a wide range of concentrations. We'll put range of concentrations. Like we can have Kool-Aid that is weak Kool-Aid or strong Kool-Aid, depending on how much Kool we put in it. But with water, it has to be what? This has a set ratio, something that's called the law of definite proportions. Law of definite proportions. What's the set ratio of the elements in water?
2 to 1.
Yeah, H2O. It has to be H2O. What if it's H2O2?
It's not.
Not water. It's hydrogen peroxide, which is a completely different thing. And if you drink it, you will vomit. Whereas if you drink water, you probably won't vomit, or at least not right then.
What is range of...
Concentrations. So they have set things that make up a homogeneous solution. There are set things that make it up, but they could have any range of concentration. You can have a concentration of 0.0001%, or you can have a concentration of 99.999%, and anything in between and anything outside of that, really, because it's about concentrations. So what are some properties of matter? Let's break up the properties. First of all, what's a property?
It's a state.
Okay, that would be an example of a property, but what in general, what is meant by the word property? What's a property of Natalie?
My hair.
Yeah, they're the things about her. The properties are the things about her. The color of her hair, the color of her eyes.
My great personality.
The great personality she has, she growls. My great personality. Yeah, those are the properties of Natalie. So properties of matter are just things about it. So we can break down properties of matter into its physical and chemical properties. The easy way to do this is that its physical properties are things that exist about it, not all the time, but things that are true of that thing itself. Whereas the chemical properties involve how it reacts with other stuff. Involves... Have you ever used this abbreviation before in this class? RXNS? No? Okay, well here you go. This is chemistry and it's all about chemical reactions, or a lot of it is. And this is an abbreviation for reaction. RXNS is an abbreviation for reaction. You remember that, girls? From when you were in here?
What?
You remember that we can abbreviate reaction as RXN? Yeah.
Have you been going to teach them the song?
Oh, it won't be yet. Well, it's this month though, isn't it? Oh, I think it's on a Saturday this year. We're talking about Mole Day, but that we're not going to do it. It's a Saturday. Anyway, so let's get some examples. Let's think about my this. Look at.
It's dirty.
Oh, okay. What kind of property is that?
Physical. Yeah, it is a physical.
Yeah, well, let's leave that one off our list, actually. That's not what we usually talk about. You're right, that is a physical property, but it's not one of the physical properties we usually talk about in chemistry. Blue, so it's color.
Soft.
Sure, we can put texture on here. What else?
It's shape.
Shape.
Smell. dirty. Expo marker.
Yeah, it smells good. Smell. What else?
And then I do these.
Well, I'm going to run out of room. Let's have one more. What's another physical property it could have?
Temperature?
Okay. What are some chemical properties it probably has? Those are a little bit more difficult to think about probably, but...
Is it flammable?
Yeah. Flammability, which is really describing how it reacts with oxygen and at what temperatures it reacts with oxygen. Flammability, what else?
Like solid, liquid, gas, what's
The state of matter is actually a physical property, and that's an important one and people get confused about, so let's make sure to put that in the physical column. But state of matter is a physical property. In this case it's solid. What else is a chemical property though? We have how it reacts with oxygen, which is what we call flammability, but how it reacts with anything. How it would react with acetone, for instance. I think it probably dissolve. I think it's polyester. But reaction with whatever. How it reacts with something else. How it reacts with chlorine would be a chemical property. But it's the kind of reactions that occur to it are chemical. As far as I know, the one that commonly comes up that we have a special name for is flammability. But other than that, it'll just be how it reacts with whatever. Okay, and then in the same way that we have physical and chemical properties of matter, we also have, you remember from your reading or from your vocab, changes. And we have physical, I'm holding my marker really weirdly, and chemical changes. So once again, the chemical changes, in the same way that chemical properties dealt with how it reacts with thing X, chemical changes are caused by chemical reactions. Caused by reactions. What might some physical changes be then? If chemical changes are caused by reactions, what would be kind of a cheat code that we could use to tell whether this has occurred? If the what changes about it?
The
color?
Not
Wait, what are we
always.
talking about?
What would be a way we can tell if a chemical change, which is caused by a reaction, has occurred?
Smell.
Possibly. And color could be, but those aren't necessarily. The smell of this has changed since I started using it, even though a chemical change hasn't
What
occurred.
about
The color has changed, even though a chemical hasn't occurred. But what must change for a chemical change to occur?
Stage.
Not always. What?
Hannah's got
What is it?
the arrangement of the...
Yes, be more specific though, because
atoms?
let's just put composition here.
Okay.
Change. You're kind of right. Change in composition. What it's made of has to change. If this occurs, what it's made of has to change. If we burn it, is it still made of polyester? No, it's completely different stuff. It's a little bit of ash, but mostly carbon dioxide and water. If we react it with chlorine gas, would it have the same chemical composition afterward? No, because that's a chemical change has occurred. But what kind of stuff could we do to it that would make it so it has the same chemical properties? A reaction hasn't occurred, but it still has changed. Cut it, yeah, so change in shape. I don't know why I put this, but shape, I'll just put shape change. I was going to put change in the shape, but I made my C really weird, so I turned it to an S.
You could douse it in water and in color change the
Yeah,
color.
that's true, yeah. Water does appear to make things wetter.
Mm-hmm.
Wetter? More wet?
No,
Wet 'em?
don't get into
Is that how you call that woman? Anyway, shape change. Some other physical changes that occur. This color change here. I'm not going to put color or odor or anything change as either of these because both of these could cause a color or an odor change. But if we specifically change the color by rubbing black marker all over it, then that would be a physical change. It didn't change the nature of this thing to have black marker on it, or at least not to any great extent. Shape change, a phase change though. This is the one that really, I used the word state earlier, but I'm going to use the word phase now. This one really throws people off. If we just melt this, let's assume that it does melt. I think it would actually catch fire, but presuming that it does melt, if we melt this, it's only a physical change. Okay? That one confuses people a lot of the times. If you have an ice cube and it melts, it's still water. It's solid water to liquid water, but it's still water. Questions about physical and chemical changes or physical and chemical properties? Let's move back real quick. We're going to talk a little bit more in depth about elements and compounds, but first we're going to talk about just a little bit more in depth about homo and heterogeneous mixtures. One way we can tell these two things apart is how we can separate them. let's give some examples first. How if we had, for example, if we had the sand and water, how could we separate the sand from the water?
Filtration.
We definitely could filter it. That probably wouldn't completely cut it. You know, like we'd still have the sand we got afterwards still be wet.
You can heat it and then
there you
the
go.
water.
Yeah, the water would evaporate. So in this specific example of sand and water, let's use filtration and evaporation. What if we had, the classic example would be sand and salt.
You would dissolve the salt.
Yeah, exactly. Sand and salt, we would dissolve the salt and then filter it. What if we had, I like this one too, it's a classic example. So what if we had sand? Listen, heterogeneous mixtures is not about sand. They don't have to have sand. But this becomes really handy to think about. Sand and iron filings. What would we do for that one? Magnet, yeah, magnet. A magnet would remove the iron filings, and we'd be left with two separate piles. But the key thing about a heterogeneous mixture is that we could feasibly separate these things by hand if we had to. We could pick out every single sand particle by hand from the water. We didn't want to, but we could. Same thing with the sand and salt, same thing with the sand and iron filings. These ways are much more efficient, but we could separate them by hand. What about the Kool-Aid? I'm going to get copyright struck. What about the Kool-Aid? Kool-Aid, how can we separate the Kool-Aid? The Kool-Aid from the water? Could we feasibly...
Once it's mixed together.
Right, I could not pick out every little particle of Kool-Aid, could I? But what could I do? Would filtration work? No, it's dissolved.
It's dissolved, so.
It's dissolved, so filtration wouldn't work. What could I do?
Evaporate.
Yeah, evaporate. And what really, so in this case evaporation would work, but we would specifically call that distillation. Now what we call it when we're a homogeneous mixture, a solution, is separated by their boiling points, and we call that distillation. I think that was a vocab word, wasn't it?
Yeah.
Yeah. So when we specifically separate them by their boiling points, separation by boiling points. And what we would do is we would boil our solution of Kool-Aid, and then we would capture the steam, and the steam would be what?
The water.
Just pure water. And that would run off into something else, and we collect that, and then we'd be left with just the Kool-Aid substance itself. It is annoying, Natalie, isn't it? You make me hate myself. Okay. Or more. You make me hate myself more.
It just kills me that you're saying it like that.
Yeah. I thought it was funny at first, and now I'm bored of it. I'm sick of it, too.
Watt incarnation.
There are other methods of removing the components of the homogeneous mixture, which your book mentions, but I like this one the best. I think distillation is really cool. Where else do you see the word distilled water? Yeah, because what comes out of the faucet, not only here but basically everywhere, or what's in the ground, is not pure water. And so the process of distillation is done to it, and it removes impurities. In fact, we have in the laboratory, we have a water distiller, and water comes out, pure distilled water comes out of it, but what's left behind is just the stuff that was in the water before. And so it ends up being like a little pile of calcium carbonate mostly. There's some iron and some magnesium and stuff in there too. But the whole point of using distilled water in the lab... Oh yeah, we'll look at it after this. But the whole point of using distilled water in the lab is that when we rinse things with distilled water, it doesn't leave behind the little white marks. And that's important for, so it looks nice, because that's what I like about it, but also so that if we use it in the lab, that little bit of calcium carbonate or whatever could really throw off our results too, so we only want to use distilled water for that. And then lastly, let's talk about elements and compounds. Elements and compounds. We already talked a little bit about the law of definite proportions, so we'll kind of leave that at that, but I want you to be able to do this math before we go. It's called percent composition. And it's really, I don't think this is difficult. All we have to do is percent composition equals the mass of the element divided by the mass of the compound it's in, times 100%. This should, what's the example you think I'm probably going to use for this, Lily? What will this remind us of? I use this example a lot. We talked about it for percent error too. What is this method like? Do you remember? We use this a lot, all the time, in fact.
Is it no conversion?
No, not really. But this is just like when you get a grade on your test. If you got a 60 out of 70 on your test, that's like the part that you got divided by the whole that you could have gotten. Part divided by whole times 100%, it gives us percent. So in this case, it would be mass of just the element divided by the whole compound. So if we wanted to find percent composition of hydrogen in water, all we have to do is take the mass of the hydrogen, divided by the mass of the water, and multiplied by 100%. Here's an example in your book. It says 20 grams of granulated sugar, there's 8.44 grams of carbon. So we would put in, sorry, I'm going to start this over. We have mass of carbon was 8.44 grams divided by 20.0 grams of sugar. Oops, times 100%. All we should do is divide those things, and we end up with, the book says, 42.20. Should just be 42.2%. 20.0 grams, yeah. I'm trying to make this a little bit prettier. There we go. Look how pretty. So all you do is take the mass of the element given divided by the total mass of the compound. This gets you through, I said this in the video I just made for Chem 2 also, this gets you through the skeleton of what's going on here. This is the framework on which the rest of this stuff is founded. The book, or chapter, this chapter of the book, I would say, looks like roughly somewhere between 15 and 20 pages long. We did not talk about 15 to 20 pages worth of stuff here, but this is the framework, okay? If you want to do more, where can you look? The book. You can also look this stuff up on the internet. You can look in your book, you can watch videos about this, but this is the stuff that is most important and will give you the most solid foundation. That doesn't mean this is everything. You shouldn't try to make yourself get an A on the test out of just this. What else, by the way, will you need to do on your test to get the best credit? 10 polyatomic ions by Tuesday. We'll plan on Tuesday being the test. We'll go over the chapter review Monday, because that's when it's due. And the test will be Tuesday. What if you're not here, literally 2/3 of the class? What should you do? You're here, so it doesn't really matter to you. But what should you do?
Everybody will be here.
Watch the video that we're making right this second. Study your polyatomic ions, and read your book, and make sure you do your chapter review. Bye!